Let us take a few examples. Suppose I take the old familiar example that we did in the very first lecture when we started rigid body dynamics. A rod having two masses m at distance L from the center and rotating with angular velocity omega about an axis which is at an angle theta from it. Let me take the line perpendicular to it as the x axis, line along the rod as y axis, and obviously then line coming out of the screen is going to be z axis. By symmetry you can see that these are principal set of axes, because along y the x component is 0, you will find I x y becomes 0. Similarly, you can find other components are going to be 0, except that I x x is going to be ml square times 2 ml square. I y y is going to be 0, because from the y axis there is no distance of the masses, and I z z by symmetry is going to be same as I x x, which is 2 ml square. So, the question is, what is this angular momentum? This is a rod rotating about an axis making an angle theta here with omega. This is the principal axis x, principal axis y, principal axis z. Obviously, the principal set of axis rotates with the body. Now, at this given position, you will see that omega has two components, one along the negative x axis for the body, so which is be minus omega sine theta I, where I represents the direction in the principal axis x, plus omega cosine of theta j, and there is no z component. Therefore, L vector is going to be 2 ml square I x x times omega x, which is minus omega sine theta, plus I y y, which is 0, plus I z z, which is non-zero, but omega z is 0. So, that is 0. So, L comes out to be minus 2 m L square omega sine theta in I direction, that is in this direction. Obviously, as the rod rotates, the L will also rotate, because these set of axes are also rotating with the body. They are very specifically oriented about the body, but this is L. I recall from the first lecture, this really comes out to be the value of L, because if I calculate L by summation mi ri cross v, v for this mass is going into the screen with the speed omega L sine theta, and r is L, and therefore, you get an answer for this. The angular momentum comes out to be ml square omega sine theta. For this also it comes out to ml square omega sine theta, both pointing in negative x direction. So, this really is the answer. As the next example, let us take a rectangle of width a, length b, and let it rotate about one of its diagonals with speed omega. I want to find what is its angular momentum. Now, either I should be doing L equals that whole thing I x x omega x plus I x y omega y and so on, or I can go to the principal set of axes, calculate component of omega, and then straight away write L equals I x x omega x I plus I x y omega y j plus I x z omega z k. Now, again I will leave it as an exercise for you to show that for a rectangle the principal set of axes are this. Let us call this the x axis, y axis. If I take the center as the origin, passing through the origin as this, x axis is this, y axis is this way, and z axis obviously coming out. This length is b, this length is a. So, I x x is going to be, if the mass is m, b square over 12, I y is going to be m a square over 12, and I z is going to be, by perpendicular axis theorem, I x plus I y. This is omega. So, let me call this angle theta. Then omega has an omega x I plus omega y j, where omega x is omega sin theta in the negative x direction plus omega cosine theta in positive y direction. Sin theta and cosine theta are easy to calculate because these distances are known. This is b by 2, this is a by 2, and this is going to be 1/2 square root of a square plus b square, and therefore sin theta is equal to a over square root of a square plus b square, cosine theta is equal to b over square root of a square plus b square, and therefore I have omega x as equal to minus omega, this is theta, a over square root of a square plus b square, omega y is equal to omega b over square root of a square plus b square, and therefore L vector is going to be m b square over 12 omega a divided by square root of a square plus b square in I direction with a minus sign plus m a square over 12 omega b over square root of a square plus b square j. So, this is not parallel to omega, it could be in some other direction. What you notice in these two examples is that if L is written as I x x omega x I plus I y y omega y j plus I z z omega z k, L is not parallel to omega unless all these i's happen to be equal. So, in general, for example, in this rod example, omega was this way, L was this way. In the rectangle example, omega was this way, L could be at some other angle, either this way or this way, depending on A and B. So, L and omega are not parallel, and L rotates about omega, and this gives rise to very interesting dynamics, as we will see in the coming few lectures.